So just in previous video, we have seen that how to use this matrix factorization technique to convert some word to vector. We have seen it. So by simply using the SVD singular value decompositions problem, we have decomposed some co-occurrence matrix and based on the eigenvalues, we have convert this thing into a some vector. We have seen this thing. So that thing that we have seen to convert a word to vector. Word to vectors, we have used simple here the matrix factorization technique. Mainly we have used here singular values decompositions technique and the SVD that we apply on the co-occurrence matrix. We apply here co-occurrence matrix and apply the SVD. We have seen it in just in previous video. Now let's see how to convert, how to use this matrix factorization techniques to find some faces of human. Let's see it. And in the end of this video, we'll see through a practical example. So suppose we have some image data. Let we have some image data. So our job is, or task is that we have to do, we have to find the eigen faces. Okay. So now the question is, what is eigen faces? We have to find the eigen faces. So this is the task actually. The question is, what is this eigen faces? What is this eigen faces? So eigen faces it is a early technique for face recognition. You can treat these things like a eigen vectors of human faces. You can like these things. Actually, this is a very old technique. Okay, in early techniques. It's a very old technique for face recognition. And the technique that we have to apply here, instead of SPD, here we have applied the concept of PCA, principal component analysis. At the end of the day, both are the same things. Okay, just in PCA we have applied the covariance matrix. Here we have applied this indirect matrix. That's the thing we have seen. We have already known this kind of. So now let's see how to detect this from the image data. How to find these eigenfaces. Okay, and we will got using this simple technique. We will got a very interesting result. We will see at the end of this video. Now let's see. So suppose let we have collected some amount of image. Okay, we have collected 400 image data. We have 400 image data. We have somehow we collect this data. Now the first thing that we have to do after collecting this, and the one thing that always remember, the image that we have collected is it's a 64 cross 64 pixel image. (64 cross 64 pixel image) means, I think it will be better. Pixel means, the image pixel means, if you zoomed in some image, then you see some kind of square, and its square content the color of that block. Okay, such kind of there have 64 columns for this image, and also 64 rows for that image. Okay, and it's a human face actually. You have to find the eigenvalues of a human face. That's the job that I do. Okay, that it is a 64 cross 64 data, means it is a square image. First thing, it is a square image. Okay, so how to, first we have to convert somehow this and this image into a vector format, then we can apply. Now let's see how to convert this image to a vector format. So to convert it, we have 64 cross 64, image size is 64 cross 64. So if we multiply this 64 into 64, you got 4096. Okay, means the number of cells that I have in this matrix, each image is 4096 number of cells have. So somehow we have to convert this 4096 cells into a vector format. Now let how we'll convert this thing. The interest thing is to convert its vector into a convert each image into a vector. So we have to take the h64 we have to take h64 row, means the vector size will be look like this, and here in first column they have 64 element, first row. In second row they have 64 element. In third row they have also 64 element. Like look like that. At the end of this also they have 64 element. Look like this kind of image, and these are the pixels of the SGB. Somehow we have to convert this thing. Suppose let's it is a R1. I think it's zoom in. Okay. Let it is a R1, row 1, it is a row 2, let it is a row 3, let up to it is a row 64. Load 64, somehow it is. Look like this. Now our job is we have to convert this matrix into a vector. Okay. To a vector. Now the first we take the first row. First we have taken the first row and put it here somewhere. This is the row 1. Now we will take the next row and put it here, R2. Now we will take R3. Look like that. At the end of this vector we got R64. Okay. So in each row they have 64 columns. Look like 64. Here also they have 64 columns. Here also they have 64 columns. Here also they have 64 columns. Okay. So how much column total we have? So 64 into 64. So total the dimension of this vector. Now the dimension of the whole vector is 4096. 4096 of this vector. The size of this vector is 4096. Okay, I think you got the idea how this image vector has constructed. Okay, so this vector is responsible for single one image 1. This vector is responsible for single image. So we have how much image? So also for image 2 we can convert image 2 into a vector, like look like this. Those who have 4096 cells. Similarly we have how much? 400 image. So 400 image, we got such kind of cell. Look like this, some pixels of the edge. These are the pixels. These are the pixels of edge. Okay. Now the questions is how to construct the vector, how to construct the matrix. So the matrix that we have to construct here is to look like this. Look like this type. Since each row is responsible for each image. here image, here we have taken only 400 image, and each column is responsible for each pixels of each image. So 1 2 3, how much pixels we have in a single image? 4096. The dimension for this matrix will be how much? Image row 400 into 4096. And if we consider these things in 400 product, and this is as a m, I think you got the idea how this image has been converted to a matrix form. This is a simple idea that we have. Okay, now we can simple, you converted this image set into a matrix set. Now we can easily apply these things per PCA. The same things also. First thing that we have to apply, since we are interested to apply the PCA on to find the eigenfaces. So for PCA, first we have to compute the covariance of A. The next state that we have to do after computing this matrix, we have to compute it. Suppose let's, instead of using M dimension, let it is a D. So the dimension of the ND. So the value of this A is, now that we have to first calculate the covariance. Covariance of A. The covariance of the A, the dimension will be S T cross T. We have already seen how to compute the covariance matrix. We have already seen. The covariance of X will be T cross T. Now the D cross D is a square matrix. We can easily decompose it into the PCA. Suppose let we got this type of, by sample using the PCA technique onto it. We have calculated this one. The dimension of the W will be what? D cross D. Dimension of the sigma will be what? D cross D. Similarly, D W transpose D cross D. Okay, by simply using this PCA technique. Now, what is W responsible for and what is sigma lambda responsible for? Let's see what is its significance. So suppose let W is here, look like this. And the column vector of the W will be the eigenvector of the eigenvalues of is look like this. The eigenvector to W is vector 1, vector 2, such kind of, they have a vector T. These are the eigenvectors. Okay, these are the eigenvectors, and the eigenvalue will be here. Look like this. Something look like this. Means this value will be lambda 1, lambda 2, lambda 3, sorry, lambda D. Okay, this value is look like this type of value we got. Sorry for this. So the upper diagonal matrix, upper diagonal, the value will be a 0, and these are the 0. And the relationships, all the relationship of the eigenvalues is look like this type of relationship. I have lambda greater than is equals to lambda 2 greater than is equals to lambda 3. These are the relationships. Already we have built this kind of. Now, the first thing, this is a D-dimensional. This is the D-dimensional, here D is the 4096. So somehow we have to reduce this dimensional. So means we have to neglect the lambda D's, the lambda I's that have the lower values. Okay. So that we have to reduce the dimension of this city. So means somehow here we have to take the D, we have to convert the dimension of the convert this d dimensional to into a k dimensional. Okay, where this k is smaller than d. This is the thing. Means we have to neglect those eigenvalues, those smaller eigenvalues. We have not to consider into our data. We have to neglect it. So let we have to take here up to somewhere lambda k. Here also we have to neglect up to k what. Okay, we have not considered into this calculation. To remove it. Similarly, where else? Same thing that we have seen. We have not considered it in our data. Okay. So this is the simple. This is the dimensional reduction that we have applied here. We have to reduce the dimension. We will reduce the dimension of this vector. Okay. Now the next step. This is the first. This is the first thing that in this step. First step. First, we have to compute the covariance matrix. After compute it covariance, in second stage we compute it. We play the PCA and we compute W lambda. And after third step, we have to reduce this D. We will reduce this D. Okay. Now, after reducing it, we got the matrix look like this, such as WK. This is the approximations of the W. Here, dimensions of the W is this. Here, the W hat. Let W. So, the vector is what is W1? Let V1, V2, somehow look like this. They are have k vector, means we have considered only k eigenvalues. Okay. Now, this is the responsible for top k eigenvalues. These eigenvectors are responsible for top k eigenvalues. Okay. Eigenvectors. These are the eigenvectors. Okay. Now, in fourth step, the fourth step that we have to do. In fourth step, we got A. We got A. A will be our this matrix. Now, the value of the A will be what? The value of the A will be n cross D we have, and that the value of the W that we got here. What is the value of the D? They have how much dimension they have? Let's just see it. W D cross D means they have D dimension. D dimension. So we will neglect this K. There have no information. Now the W hat that we got here, its dimension is D. Here its dimension is D cross K. Now we have to multiply this A to this W hat. Its dimension is D. Now this matrix that we called, this is the n cross K matrix. Okay, this matrix that we got here, this is called the eigenfaces of each eigen. Now let's look which what type of matrix it will be look like. Something look like this. Since they have n rows and they have k column. Okay, so first how much column they in, just see the original A. In first the column of this 4096, here k must be less than is equals to small value it is. So in A the D is equals to 4096. but in a hat, in a hat, k is less than is equals to d, smaller value. So simple, just see it. We can easily reduce, and the same thing, this column is responsible for what? It's always you have to remember, this column is responsible for image 1, this responsible for image 2, these things has been responsible for image 3. Look like this thermals is responsible for image n. So here n is what? N is 400. We have taken the 400 images here. Okay, here n is equals to 400. So this h row, this h row vector is responsible for the dimensions, the matrix representations of the h image. Here also h row vector is now a vector representations of the h image, but the main advantage is we have the dimension of the, here the dimensional is, here the dimensional is 64 cross 64, but here dimensional is reduced. Okay, so here the dimensional is, write it. So the here if you consider the image 1, here the dimensional here will be 2, 3, 4, 5, 6. Look like this. Here up to k. Now here we have to take on the module. First we have taken the 64 and consider is a R1. Now we will consider the next 64 R2. Means it's depend on the how much size you will interest to build. Okay, just according to this k value we will build our image. Okay, I think you got the idea how to convert this image to a some value, and this image that we got here from here to here. Now from here to here, the image that we got, let's take it's the r test 1, r test 2, somehow look like. So here it will be r test 1, r test 2. Look like this image. Suppose let's take, we call some image, different image test. So this image is called the Eigen faces. Eigen face of image 1. Okay, I think you got the idea how this image has been represented. I think I'm doing some mistake here. I've done some mistake. Okay, no, okay, everything is okay. So after multiplying this value, we got this n cross k. K is smaller than this. So the matrix that we got here, this is called the image faces. Means the informations that carried, so the information that carried on the main image, this in the main image. So the after reducing them some pixels from that image, we got some important informations from that image. So these important informations that are the smaller than the original image are called the eigenfaces. Okay, so now let's look it through a real life example. Okay, I think then it will be better for your understanding. Now let's see how this algorithm that we have discussed is now applicable on real data. So the block that I have showing here, I am giving the link down the description section. If you have time, please, I suggest you please read these blocks. It's a very nice block, and very nicely they have explained everything. Actually on the training they have considered 1000 image, and in image contains 64 by 64 pixels data. And by simple using the build and the matrix they have built using this thing that we have seen, the matrix we have built a matrix using this data, a matrix they built, and on the a matrix they have used the principal component analysis PCA, PCA principal component. And after this taking, they have considered first 50 eigenvectors. First means first 50 eigenvalues. Actually, here k is equals to they have taken 50. Okay, here k is equals to they have taken 50. Now, after taking the 50, that the matrix they got, and after drawing the eigenfaces, that's look like this. So this is the original picture in thousands. After taking the 50, 150 k is equals to 50, the eigenfaces that's got it. It's most of the information, important information that's shown. Just see it. H faces here, original faces, and this is the after taking the k is equals to 50. These are the eigenfaces actually. These are the eigenfaces. Okay, this is the original faces and this is the eigenfaces. Just see it. This is the first value. This is the first eigenfaces. This is the second eigenfaces, third eigenfaces. Look like that. Means just see it. So here just convert, keeping just 20 times less informations they have taken here. Just see it. So we get to keep 20 times less data than before. At first they have considered 1000 images, and now they have considered 50, only 50 eigenfaces. Okay, that's the first thing. Now let's go below. Now in this case they have improved something. So in first cases they have taken 50. Here they have taken 250. Let's see. When we have taken the 250, when we have taken it's the 250. Okay. When we have taken it's 250, then let's see it. Its pictures look like better from before. Here we have 50k. K is equals to 50. Here k is equals to 50. And here k is equals to 250. It's look like more sharper. Here let's see. Here they have taken k is equals to how much? Actually 100 eigenfaces they have taken. Means k actually they have taken all the these things are all the same kind of faces. Okay. So this is the main thing. I think you from these examples, I think I suggest you, in description sections I will give the link of that blog. Just read it. Okay, just see this. They just take on they also give the where will the data set. Just download it on your computer. Just download this data set. Where somewhere they have given the link how they collected this data. Somewhere here, I think. Yes, right. These are the data. This download this GIF file, and they have. I think they have only taken the first 100 steps. Okay, first 1000 steps they have taken, and first 1000 steps after they have applied this technique and converted the dimension will be 64.6 and 1000 into 4. Already have seen this. Converted it and it applied this principal component analysis through this code and just taking the average eigenfaces. It's the average value, all the combine all the value. So these are the eigenfaces. First eigenfaces, second eigenfaces. I think in such cases they are taken only 15. Here we have taken only 15. Only 15 eigenfaces. I think let's look like this. How much blurrer it is. In the first eigenfaces they have taken captured. They try to capture the most important ones. Okay, these much. And here they have taken the first 50 eigenfaces. K is equals to 50. Here taken k is equals to 250. Here taken k is equals to 2000. More or less similar. I think you got the understand from this explanation. Just in your time, just read this blog. Okay, and try to yourself in your own computer. So it's not a very easy task. Very easy. Just a simple Python application. They have applied simple Pythons, nothing else. Just download the images and just run it on your own computer. Okay. Now let's conclude this lecture. What we have learned. We have learned that first we have to convert edge images set into a vector format, into a matrix format, set of 400 images that I have taken as an examples. We have converted into the matrix format, and on this matrix we have applied the PCA technique. After finding the PCA technique, we have to choose the K, means K is the hyperparameter. Okay, K is your hyperparameter. How much information so you want to store, that's actually depends on this K. And this according to this basis of the K, we have to find the eigenfaces. Actually, eigenfaces is, if you just pick up these things, eigenfaces is this thing. Just see it. The W hat that we got. The W hat that we got. What is W hat? It's contain the eigenvector. It's the V1 first. Yes. It's the first little dimension 1, 2, 3 up to D. Yes, this is the first eigenvector. V2. It is the second eigenvector. Look like that. We have taken consider K hyperparameter. Means K less than is equals to D. K eigenvector we have considered. And H eigenvector contains the T dimension. Okay. Here H Vi belongs to RT. Now the eigenfaces is, if we convert this, actually this is a D and D is what here? Here D is 4096. If we convert this thing into a image format, this Vi will be converted. Here it will be first 64 data. This will be the second 64 data. Look like this. This is the 64 data. So the single image, single Vi is converted to be a 64 cos 64. So this image that we have converted over, this image is called the eigenfaces of the image I. It's called actually ith eigenfaces. Yeah, I think you got the ith eigenfaces. So here I will be from what to what? Here I will be 1 to up to K. It depends on the K, how much K we are interested to find. So first image that we got here, first eigenfaces will be considered with this image will capture more information from our whole data set. The second will captures less amount of information from the first one. So these are the eigenfaces actually. I think you got the idea how these things. And after finding these eigenfaces, if we multiply this to our original matrix, you got this kind of matrix that we have seen on that example. These things are called actually eigenfaces. These image are called the eigenfaces. Just try it in words yourself through this block. Okay, just using these data sets and try it in yourself. Then it will be better for you for better understanding. Okay, now the questions that's come into our mind, sir, how will choose the what will be the best K? What will be the best K? So it depends on the variances. If you remember the dimensionality PCA chapter, if you remember, then in details we have discussed. So the lambda 1 means the first eigenvalue, lambda 2 is our second eigenvalue, third eigenvalue. We have calculated amount of variances that explain it, how much information they are have in that eigenvalues, means the amount of variances it explains how much information they have explained. Hence they are simple. That's the actually how much means if you just plot it, look like this. Plot the eigenvalues, lambda 1, lambda 2, lambda 3 up to lambda k. It's lambda d up to lambda d dimension. If you're not considering the hyperparameter, if you consider all the parameters, then we will see if you plot the accuracy, means the variances here. So this variance picture will be look like this type. Sorry for it will be look like this type picture we got. Yes, after some stages it's stabilized, means here somewhere here it takes this much information. Suppose let's take this much 90% informations here have up to, suppose let's take some lambda k. So up to lambda k, first lambda k eigenvalues contains 90% informations, and only rest of the 10% informations content by nkd, means how much eigenvalue we have first, sorry for that, n eigenvalue, sorry, n dimensional data sets, n eigen, how much eigenvalue for here, sorry, d eigen d, w, how much eigenvalue, d eigenvalue, sorry, right, okay, don't be confused, here d eigenvalue we have. So only here, so rest of the d minus k eigenvalue contains 10% information, just it contains only 10% informations, this area. Okay, the 90% informations are contained by this first k eigenvalue, the first k. Hello, these are the things that you can easily find it. Just revisit this chapter, dimensional reduction chapter, then you can easily got it, how to find these variances for each eigenvalue. That's not a hard task. So by simple using this technique, how much information we want, actually according to this we have to choose this k, what will be the value of the k. I think you got the idea from these discussions, what is eigenfaces and how these things are actually applicable to detect the human face, and how to reduce the image dimension of the image. Means the main motto of this eigenvalue is actually, if you summarize this thing, the main motto of the eigenvalue is to collect the information, how much information we have required. Unless calculated a total whole big data sets, if we calculated the some small amount data sets and that contains most of the information, that thing actually helped by the eigenvalue. That's the main job, that's the main applications of the eigenvalue everywhere. Okay, now in next lecture next video we will see how the matrix factorization techniques applicable on Netflix movie recommendation system. Okay, we'll see these things in live practically, we will see these things in next video.